All right. So the last couple chapters have been focused on magnetic phenomena, magnetic fields, magnetic forces, and now we're going to talk about an extension of the magnetic phenomena that we've been talking about, and this is the idea of induction. And induction, the idea of it, or the phenomena, was first discovered in the mid 1800s by Michael Faraday. And one of the experiments that he was doing, or sort of accidental discoveries that he made, was that when he took a magnet and sort of pushed it through a closed loop of wire, he noticed that current started flowing in the wire. And so this picture here kind of demonstrates what Faraday was doing back in the 1800s. This first picture over here, we've got a galvanometer hooked up to just a loop of wire, and we've got a bar magnet being sort of pushed into the loop. And as this is happening, the galvanometer deflects, indicating that there's current flowing in the wire. And if in the next picture you pull that same magnet back out, the galvanometer deflects in the other direction. And if you change the orientation of the bar magnet and push it into the loop again, now it deflects. The galvanometer deflects to the left, and when you pull it back out, it deflects to the right. And probably most importantly, if you just hold the magnet near the loop of wire, no current is induced or is flowing through the loop. It's only when you move the magnet into or out of that loop that the galvanometer deflects. And so there's something fundamental about the motion of the magnet relative to the loop that induces this current. And that's what we want to explore. So to explore this, we need to bring up the idea of magnetic flux, which is identical in every way to electric flux that we talked about previously. The only difference is now we're talking about the magnetic field rather than the electric field. So the magnetic flux is just take some surface, and the magnetic flux is some measure of the field passing through the surface. And so if you want to actually calculate the magnetic flux, you've got to do this integral, B dot dA, where the direction of dA is perpendicular to the surface area. And so this picture over here gives you some idea of what we're talking about, right? Remember when we talked about electric flux, I gave an example of like rain and a bucket and trying to catch the rain in the bucket, and how the orientation of the bucket opening, right, determines how much rain flux, right, you're able to measure or that exists. So the unit for magnetic flux is the Weber, and a Weber, just coming straight out of the units for the expression, is a Tesla times a meter squared, right? So a Tesla square meter. So the induced current that we're seeing in this picture, that is a result of the magnetic flux through the loop changing. And so if there's an induced current in the loop, then that must mean there's an induced EMF or an induced battery in the loop. And Faraday's law is how we can quantify what that induced battery or induced EMF happens to be. And so Faraday's law, I've got it written here. So we'll just read it out, and then we'll talk about what it means. The induced EMF is the negative change in the magnetic flux per unit time. What does that mean? Well, it means this right here. Take the time derivative of the magnetic flux. The negative of that quantity is the induced EMF, right? So that induced EMF will then drive a current in your loop, because the current induced will then be the EMF divided by whatever the resistance in your loop is. So we've got a picture down here at the bottom that demonstrates this a little further. I've got on the left I've got a circuit, I've got two circuits next to each other. Initially, what I'm going to do is I'm going to close the switch here. And when I close that switch, well, I've got a battery, and so then there's a current that before I close the switch, there was no current. But when I close the switch, now all of a sudden there's a current. And if you look at the loop, right, the current will be going in that direction around the loop. So before I closed the switch, there was no magnetic field produced by the loop on the left because there was no current in that loop. Once I close the switch, now all of a sudden there is a current, and so there will be a magnetic field pointing this way. And if I was being true to the field lines, I might draw them like this. Something like that. But they're pointing from left to right inside the loop. So if you think about the right loop, well, before the switch was closed, there was no magnetic field through the right loop. Once I close the switch, now all of a sudden there's a magnetic field pointing that way through the loop. So the magnetic flux through the right loop has changed. It was 0. Now there's some amount of magnetic flux corresponding to the B field pointing to the right. So what that means is that the magnetic flux through the loop changed. There will be an induced EMF produced in the loop, and so there will be an induced current. And the induced current is going to be such that the B field produced by the current works to oppose or minimize the change in flux. And so you can see the current is drawn going around this way. That would generate a B field inside the loop in the opposite direction. Let's look at the middle picture. The switch was closed, and so this is just some time later. So the current in the left circuit is just some constant value. So there is a B field generated by the left loop, but it's constant because the current isn't changing. And so what that means is there's no induced current in the right-hand loop, and you can see that by the galvanometer not deflecting. Now, at some point, we open the switch, and so all of a sudden there's no current in the left loop. So before we open the switch, there was a B field pointing this way, and then we open the switch, and that B field goes away. So now all of a sudden there was a change in flux in this loop again, right? There was a magnetic field pointing through the loop, and now there isn't. So that means you need an induced current to produce a B field that opposes the change. So the B field originally was pointing to the right. Open the switch, the B field goes away, so the induced B field needs to point to the right. That means you need an induced current going around in that direction. All right, so the reality is that discussion in the last set of pictures was sort of difficult to follow. The idea of determining the direction of the induced EMF and the induced current from Faraday's law can be a little bit challenging. And so what we typically do is we use what's known as Lenz's law to identify the direction of the induced current, and then Faraday's law to determine essentially what that current is, right? So Lenz's law is a qualitative thing. Is there an induced current? What's the direction? And then Faraday's law will allow us to figure out what exactly is that current value. So Lenz's law is the idea that if the magnetic flux through a loop is changing, then you have an induced current. And the induced current is going to be in the direction such that the B field produced by that induced current is opposing the change in the magnetic flux. And so these two starred regions here, these two statements, that didn't work. So these two statements are the essence of Lenz's law, and this is typically how I approach a problem, first I check to see, is the magnetic flux through the loop changing? If the answer to that is yes, then there must be an induced current. Or conversely, if there's an induced current, then I automatically know that there must be a change in the magnetic flux through the loop. So that's step one. And then the next step is, all right, what's the direction of the induced current? Well, the induced current is in the direction so that the B field inside the loop that's been produced by the induced current, that the induced B field that gets set up opposes or offsets the change in the magnetic flux. And so what does that mean? Well, let's check out this picture down here. So in the left picture, I have a bar magnet, and the bar magnet is moving towards the loop. And so the magnetic flux through that loop is actually increasing. The B field is getting stronger. The area, of course, of the loop is not increasing or decreasing, but the strength of the B field is. And so that B field is pointing, if you can see this, that B field is pointing in that direction, essentially. So that B field is getting stronger. That means I need an induced current so that the induced B field offsets that increase in magnetic flux. So I need an induced B field pointing back to the left. That'll only happen if the induced current is in that direction. Now let's look at the other picture. So here we have a magnet switched around, so now it's the south pole moving into the loop. So same exact idea, the magnetic flux is increasing, but now the magnetic field is pointing this way. So the magnetic field is getting stronger, so the flux is increasing. That means we need an induced B field that offsets that increase, so we need an induced B field that's pointing in that direction. Well, how do we get a B field pointing in that direction? We need the current in the loop to be going that way. Right? So using Lenz's law, you can immediately determine whether or not there's an induced current and what the direction is, and then you can move over to Faraday's law, actually quantifying what that current has to be by estimating or determining the rate of change of the magnetic flux. Okay, so let's look at an example. Here I have a circular coil in a changing magnetic field. So we're given the radius of the loop of wire. We're told how the magnetic field is changing, right? So the B field the strength is decreasing. Now, and what we want to do is calculate the induced EMF. So the induced EMF in the coil at different times. And then for the second part, we're going to determine what the induced current is using Ohm's law. So before we start, we're going to use Lenz's law to determine the direction of the induced current. So we have a B field coming out of the page in the picture, but that B field is getting smaller, right, in strength. So it's getting weaker. So that means the magnetic flux through the loop, right, this is the area, but the B field is getting smaller. So what that means is that the magnetic flux is changing. The magnetic flux is getting smaller in magnitude or amount. So we need an induced current to offset that decrease in flux. So we need an induced B field coming out of the page, right, to offset that decrease. So that means we need a current that's going around in that direction. That'll give us a B field out of the page. So this must be the direction of the induced current. All right, so that's from Lenz's law. Now the question is, well, what is that induced current? So we're going to actually quantify this using Faraday's law. So let's see what happens. So first off, Faraday's law right here. So the magnetic flux itself, we've got to do the integral B dot dA. Well, B is constant, at least it's uniform spatially, right? It's changing with time, but spatially it's uniform. It's the same value everywhere inside the loop. And so then dA is just the integral of r d theta, where we're basically going to end up with pi r squared, the area of a circle. All right, so that's what we've got at the end. So now I'm going to plug in b, because b has a functional form which depends on time, and so that's what I've got over here. All right, so this is the magnetic flux through the loop at any given time. So it's got the time dependence in there, and then I need to take the derivative with respect to t, and when I do that, I get that the EMF induced in the loop is time dependent, right? So at different times it'll be a different value, and that's because the rate of change is not constant. And so I've got this expression for the induced EMF, and now all I got to do is plug in the values for t. So at t equals 0, I get 6 volts. At t equals 0.005 seconds, I get 4.7 volts. And at 1 second, I get 0.04 volts. Right, so at those different times, there's a different EMF induced in the loop. And then using Ohm's law, you can immediately get the induced current. So initially it's 0.6 amps. It's dropped to 0.47 in the first 0.005 seconds. And then after 1 second, it's down to 0.004 amps. So that is sort of the general approach. Lenz's law tells me immediately what the direction of the induced current needs to be, and then Faraday's law allows me to quantify it. All right, what is the induced EMF? What is the induced current? All right.